Welcome back to The Explainer. Okay, today we are embarking on a true mathematical expedition. We're going to demystify Chapter 7, and that means we are tackling integrals. Now, I know, if you've ever felt a little intimidated by those swirly calculus symbols, you are not alone. But don't worry, we're going to build this up step by step until it all clicks perfectly into place. It's the absolute backbone of advanced science, engineering, and economics. So let's get right into it.
Okay, let's dive into this with a quote right from the text that I absolutely love. James B. Bristol put it perfectly. Just as a mountaineer climbs a mountain because it is there, so a good mathematics student studies new material because it is there. It's a fun, slightly humorous hook, right? I mean, sometimes we tackle tough math problems simply for the thrill of the climb. But as you'll see in this explainer, the view from the top of this particular mathematical mountain, it gives us a totally new way to understand the physical world.
So here's our mental roadmap for the ascent today. We've got 6 parts. First, the mountain of integration. Second, reverse engineering the derivative. Third, the standard formulas. Then, techniques of integration, finding the area, and finally, the fundamental theorem.
All right, kicking things off with Part 1, the mountain of integration, embarking on our mathematical expedition.
Now, what's really interesting about this is putting a human face to the abstract symbols we're about to explore. Before we look at any equations, we really need to understand the human motivation behind this branch of calculus. This right here is Gottfried Wilhelm Leibniz. He was a brilliant mathematician from the 17th century, and he, alongside Isaac Newton, is credited with pioneering calculus. But they didn't just invent this math to torture future students, right? They did it out of a sheer effort to solve the massive theoretical and practical problems of their day. They were literally trying to decode the universe.
Moving right along to Section 2, reverse engineering the derivative, or putting the puzzle back together.
So, if you're already familiar with differential calculus, you know how to take a function apart. Calculating the slope of tangent lines or finding the instantaneous velocity of a moving car. It's really about breaking things down to a specific instant. Well, integral calculus is the exact inverse of that. It's about putting the puzzle back together. You're calculating the area bounded by a graph, or finding the original function when you only have the derivative. Basically, you're taking the pieces and building them back up into a whole.
So the crucial point here is a concept called the antiderivative. Sometimes it's called the primitive. If a function gives you a derivative, integration is simply the process of working backward to find that original function. It's kind of like being handed the pieces of a shattered vase and figuring out exactly what the vase looked like before it broke.
Now, you might be wondering, why does this actually matter outside of a textbook? Well, look at this real-world physics application. Let's say you have the data for the instantaneous velocity of an object, maybe a rocket shooting into space, at any given microsecond. Integration allows you to definitively calculate its exact physical position at any instant. You're literally using the rate of change to map out the actual journey. I mean, that is incredibly powerful.
That brings us to Section 3, the standard formulas, essentially the language and rules of the road.
Let's quickly decode some of this mathematical language. That elongated S symbol, that's the integral sign. The function inside, f of x, is called the integrand, and the dx simply tells us that our variable of integration is x. But I want you to pay special attention to that capital C at the bottom. Since the derivative of any constant number is 0, when we reverse engineer a derivative, we absolutely have to add this constant of integration, that's c, to account for any flat numbers that might have just vanished during differentiation. It's basically our mathematical safety net.
And here is where your prior knowledge pays off beautifully. Look at how these line up. You don't have to memorize a whole new set of rules from scratch. If you know that the derivative of sine is cosine, well, you get the integral formula for free. The integral of cosine is simply sine plus our constant c. Same goes for e to the x. If its derivative is e to the x, its integral is e to the x plus c. They are literally just two sides of the exact same coin.
Furthermore, we have these properties that act as a sort of rule book for simplifying messy equations. Like, if you have an integral of a massive sum of different functions, you can actually break it apart and integrate them one by one. And if there's a constant multiplier, a real number k, you can just pull it right out to the front of the integral sign. These properties are lifesavers because they let us manipulate super complex expressions into manageable, bite-sized pieces.
All right, Section 4, Techniques of Integration. Let's expand our mathematical toolbox.
So the text outlines 3 primary problem-solving methods here. First up, integration by substitution, which lets us swap out a really complex part of an equation for a simple variable, just to make it look like a standard formula. Then there's integration using partial fractions, a brilliant way to break down clunky rational functions into simpler fractions. And finally, integration by parts, which helps us tackle the product of two different functions. Now, we aren't going to sit here and solve long equations right now, but just knowing these three tools exist means you are fully equipped to handle almost any algebraic curveball thrown your way.
Moving on to Section 5, Finding the Area and the Definite Integral. Now prepare for a major, exciting plot twist in our journey here, because this brilliantly illustrates the real magic of calculus. We're transitioning from pure abstract algebra, finding those mysterious original functions, straight back into physical geometric space. The entire motivation here is figuring out the exact area of the space tucked underneath a wavy, irregular curve on a graph.
To actually do this, we define the area function, a of x. Think of it kind of like a curtain being pulled across a graph starting from a specific point A. As that curtain moves to position x, the area revealed behind it is represented by this integral. Notice how we now have limits on our integral sign. It goes from a to x. This is what we call a definite integral, and it's the absolutely crucial stepping stone to the most important revelation in our text.
Which brings us to Section 6, the fundamental theorem, the grand finale bridging the indefinite and the definite.
This is it, the climax of our mathematical expedition. The fundamental theorem of calculus is exactly what it sounds like. It is the bedrock of the entire subject. It proves that calculating slopes and calculating areas, which genuinely seem like totally different geometrical problems, are actually intimately connected. This singular realization, that's what turned calculus into a practical powerhouse, the kind of tool we use to build skyscrapers, predict financial markets, and literally send rovers to Mars.
Let's look at and see how this builds, because these two theorems perfectly support each other. The first theorem establishes that the derivative of our area function is just the original curve itself. But look at the second fundamental theorem. It says that to find the exact area under a curve between point A and point B, all you have to do is find the antiderivative, which we just practiced earlier, plug in the upper limit b, plug in the lower limit a, and simply subtract the two. F of b minus f of a. It is breathtakingly elegant. You are measuring the whole simply by finding the difference between the boundaries.
We've covered the mountain of integration today, all the way from antiderivatives to the fundamental theorem. So I want to leave you with this final thought. If integration allows us to accumulate microscopic parts to find a total measurable whole, how might you use this concept to measure the accumulation of changes in the everyday systems around you, whether that's the growth of your investments, the power consumption of your city, or even just the distance you travel over time? Thank you so much for joining me on this mathematical expedition in the Explainer. Keep analyzing, keep learning, and I'll see you next time.